Get your formula sheet out. That's 101. So there should be a section on your formula sheet just dedicated specifically to Zener power supply. So the first one, I need to make that bigger. It was bigger on my computer in the office. So we're trying to design and draw a Zener regulated power supply using the following parameters. Show all calculations. We're going to have an input voltage that's going to vary between 10 volts plus minus 10%. So first thing I'll do is what would be the minimum input and what would be the maximum. So we got an input voltage that's going to vary 10 volts plus or minus 10%. What would be my minimum in and what would be my maximum in? So minus 10% and then plus 10%. So what would be minus 10%? That'd be 9 volts. And then my plus 10% would be what? 7 volts. Okay, are you okay? Zener voltage is equal to 5.1 volts. Load will be between 0 and 10 milliamps. And I need to kind of reword this because I didn't want y'all to draw, nobody drew the whole power. So if I was going to draw a Zener power supply, I'd come up here and do this. I would start off with a power plug, and then I would come up to a what? I would probably come up to a transformer, and then I'd go to a rectifier, and then I'd go to a filter, and then I would have my Zener circuit out here. That's not really what I meant. I need to reword that. So what I wanted you to do is just draw the regulating portion of the power supply, just like we did in class the other day. So what I would do is I would come over here and I'd put my resistor. So there's RS, and then I'm gonna come over here and it's a positive power supply. So I'm gonna put my Zener in this direction right here. Draw a common, and then so this is going to be unregulated in, and this is going to be regulated out. So over here we're going to be putting 9 volts to 11 volts. I guess I should draw that the other way. Over here is going to be 11 volts to 9 volts, and this is going to be varying, and this would be my Zener. And that would be the circuit. That's the circuit right there. Nothing much to it. And that way we don't have to draw all that other stuff. And so what we're going to do is we're going to do a 5.1 Zener. And it says it's going to be one of the 4720. It's going to be one of the 4700 Zeners. So where did y'all need to go to find the information? The data sheets on Blackboard. Thank you. So y'all bring them up. I'm not gonna, I don't. And we're looking for a 5.1 volt Zener. And then we would come up with data sheets, and then 4700 series of Zener diodes. And these are all 1 watt Zeners. And then we're looking for one that's got a VZ, a Zener voltage of 5.1 volts. So we're going to use the 4733. One N, 4733, and this is a watt. It's a 5.1 Zener, which would be the VZ. Now over here on my load, I'm going to put some type of load. So what we'll do right now is just put a resistor over here. Of course, it's going to be variable, and it's going to go from 0 milliamps all the way up to 10 milliamps. So we'll be able to take the load off. Are we okay? So there's my circuit. That's all the information I need to be able to calculate this thing. First thing we're going to have to do is choose the value of RS. So give me the formula for RS out of that formula sheet. Okay, VRS minimum IL max plus IZK. Okay, so we gotta size that resistor. What's the minimum voltage across the resistor? Okay, that's something y'all gotta really watch out for. So that's like me coming over here, and I come over here and I do this, right? You understand? And I come up here and I have 12 volts. And down here, I say, okay, down here, I'm dropping 5.1 volts. What's the voltage across the top resistor? Yeah, it's not you should, you must. Because if you don't, you're going to miss everything. Okay. So we'll go ahead and calculate. So VRS minimum would be equal to what? That formula's on there too, right? Would be equal to VN minimum minus VZ, 5.1. So what's the minimum voltage it's going to have to drop? 4.9 volts? 3.9, sorry. Then we'll go ahead and calculate VRS max, because we'll have to need it later on to calculate the power in the Zener. This is going to be to 11 minus 5.1. What's that going to give me? 5.9. And we're going to use that later to calculate the power in the Zener and also the maximum current flow in the circuit. Okay, so we're going to come in here and plug this formula in. So the value RS is going to be equal to VRS minimum. So it's going to be 3.9 divided by I the load maximum. It's going to be 10 milli plus IZK. So what's IZK for a 4733? Where are you going to find that information at? Okay, on the data sheet. That's IZK. This stands for current. Current is not in ohms. So 1 milliamp. So I'm just going to erase the 10 down here because I can do that in my head. So I'm going to divide this by 11 milliamps. So what's our calculated value for RS? 3.9 divided by 11 million. What's the calculated value for RS? It's I, okay, wait. It's I the load maximum. Now what's I the load maximum? 10 milliamps plus IZK. And we look it up on the data sheet. So IZK, so over here, and don't use resistance, right? So IZK for the 33, here it is right here. IZK, here's IZK for the 33, it's 1 milliamp. So 10 plus 1 is what? 11. You okay, Courtney? Huh? No, I'm not going to go ahead. So the 10 milliamps, the current in the load is given. So the current in the load is given. So it's going to go between 0 and 10 milliamps. But what we're going to calculate that resistor is we're going to use I the load maximum, right? You understand that, plus IZK. And where does the IZK come from? So this is going to come from the data sheet. So when I looked over here, this said 10 milli. When I looked up the data sheet for IZK for the 4733, it's 1 milli. So 10 milli plus 1 milli is 11 milli. And that's where the 11 milli came. So what value did we come up with RS? Okay, but normally what we do is round this because there's no such thing as a fractional ohm resistor for one thing. So what am I going to do with that 354? Am I going to use 354 up here? No. What are we going to do? First of all, I'm going to go back to the internet and I'm going to bring up over in course oops, wrong thing, Rich. So in the reference material, since we use this so much, I'm going to go down here and find a standard resistor chart. And we're going to use the 5. So here's 10%. We're not going to use the 10%. We'll use the 5%. And so which one would I start off with? If I'm going to round down or round up? I'm going to round down. So what would I start off with? 330. Good. So that's the one I would choose. So I go over here and I'm going to choose 330. And then I'm going to check it by multiplying it by 1.05. And what does that come up and give me? What? 346. And what we're doing is we're looking for it to be lower than that. If it's lower than that, it's fine. If it's higher than that, then we'll go one more down, right? You understand? Everybody understand that? So RS is going to be 330 ohms. And then we're through with this. Since I don't have much room up here, I'm going to erase it. Okay, so what's the next thing we need to calculate? We need to know three things about that resistor. We've already chose two of them. We've chose the tolerance and we've chosen the value, right? You understand that? Okay. So what's the next thing we need to know before I buy that resistor? The wattage. So what's the formula for wattage? PRS, right? Max, because that's when it would get the hottest. Okay. Yeah, 5.9 squared over 330. And that's one of those Watt's Law formulas you should know. What's our three Watt's Law formulas? So power in the resistor would be equal to V times I. Power in the resistor would be equal to I squared R. Power in the resistor would be equal to V squared over R. So that's three power formulas you need to know. And these are not on the formula sheet. Why aren't they on the formula sheet? Because you're supposed to know these, right? So basically the only thing on the formula sheets are the new formulas that you pick up this semester. But where did all this stuff come from? Well, we're using Kirchhoff's law, voltage law. Where'd you learn that at? DC, right? You understand that? You're supposed to learn it in DC, right? You're Courtney. And we're using Ohm's law. Okay, so what did we come up and get? 5.9 squared over 330. What's that? 106? 6, Rich. So what size would we use? Probably need to double this and then use the next standard value. So if I double that, it's going to be 212. So we'd use a quarter watt. You understand that? Yes, no? Of course, I don't think I asked y'all to choose a wattage resistor. But we'd use a quarter watt. Everybody understand that? Yes or no? Because normally what we do is we double this, and then we choose the next standard value, and we would always round up. So what is resistors? What is the wattage rating on these radial lead resistors? Which ones can you buy? So the radial lead is the ones we have. Radial lead means that the leads come out the end. So what's the standard ratings of these things? The basic standard ratings. What's the smallest we can get? We can get 1/8 of a watt. What's the next one? Yeah, quarter watt. What's the next one? Half watt. What's the next one? 1 watt, and then it goes 2 watts. And I think then it jumps up to 5 watts. And then after that, it's different. And how can you tell the wattage rating of the radial on resistor? How do you know the wattage rating? Not the color. It's not color coded. The wattage rating, the value is color coded, but the wattage rating is not color So this is something you need to learn too. So you need to be able to look at a resistor and tell what value. So this is a half watt. I don't have a quarter watt up here right now. This is a quarter watt. And we got some eighth of watts in there. I think we got some 1 watts too. Oh, no, you need to be able to. So that, what you're looking at there, the big one is a half watt. The small one is a quarter watt. And then we got some eighth of watts in there. Yeah, and you just get, no, the eighth of a watt is a little old tiny thing. The quarter watt, so we got our resistor. So what do we need to do now? We need to make sure we don't burn our zener up. So we're going to calculate the power in the zener. And if it comes up to be less than 1 watt, we're okay. If it comes up to be more than 1 watt, then we're not okay. So I had to be real careful the other day because the one I just threw out there came up to be 2 watts and it was a 1 watt zener. So we couldn't run it very long, right? Because what would happen? It would have burned up, right? Okay, so what's the formula for a zener? So PZ, power in the zener. So P is what we use in formulas to represent power. And of course, the formula we're gonna get this from is so we're gonna get PZ is equal to VZ times whatever current's going to go through it. Now, what we're going to do is we're going to calculate the current flow through it. So the first thing I want to do, what's the formula? What formula did it give y'all? PZ times what? Couldn't be IZ max. Yeah, IRS max minus IL minimum. Okay. So what's going to be the maximum current through my resistor up there? What's the maximum voltage it's going to drop? The maximum voltage it's going to drop is going to be the maximum current, right? Y'all understand that? Okay. So I'm going to calculate IR max using Ohm's law. IRS max. And this formula should be on there. It's VRS max, which is 5.9, divided by the size that we chose, not the size that we calculated, the size that we chose. 330 ohms. Yeah, but the problem is we're trying to calculate the current flow through the zener. And my formula for current flow is I is equal to V over R. Okay, what's the resistance of the zener? Say, I don't know. I don't know. It changes all the time. It's a dynamic device, right? You understand? So, but we do know that the current flow in the circuit, we know that, we're supposed to know this from DC. We do know that the current flow in the circuit is 2 different paths. So first of all, if I can calculate the current flow in RS, I know the current flow in the circuit because it's in series, right? It's called RS. It's a series dropping resistor. So if I can calculate the maximum current flow, if I can calculate that maximum current flow right there, then that's the maximum current flow in the circuit. And that's when the current flow in the zener would be maximum. Then we got to say, okay, when I come over here, I get 2 paths. So to calculate my zener current, I need to know what's this current over here. Well, the sum of these 2 currents is going to be equal to RS. So when this current flow over here is minimum, the current flow through the zener is maximum. So that's what we're trying to do. We're trying to get the maximum current flow through the zener because that's when it's going to dissipate the most power. So what we'll come over here do, and we'll come over here and say, okay, VZ, well, let's just put the values in here. I'm sorry. What's VZ? 5.1. times, and then we're going to take RS maximum. In fact, this is easy, or RS minimum. We're going to take this right here, which we came up to give what? What was this one? 17.9 milli times 17.9 milli. Now, why did because, so this is actually 17.9 minus, what's my minimum load current? What's my minimum load current? What's my minimum load current? 0. So in this situation right here, so this power supply is designed to go unloaded. You got your worksheet, right? Okay, come up here, get the cube. Here's the cube. So what's the maximum? What's our power? Huh? $91 milliwatt. So are we okay? Yeah, we're really okay. That's a 1 watt zero, that's a 1 watt zener, which would be 1,000 milliwatts, right? So we're well within limits. And that's everything. So we calculated this. We calculated this. We calculated this. And we designed our zener power supply. Using what laws? Kirchhoff's law, Ohm's law, and Watt's law. Where'd y'all learn all those at? What was y'all supposed to learn that? Let's rephrase that. DC. And of course, we erased some stuff because we didn't have enough room. I'm not going to draw the unregulated and regulated, and I'll put the value, the given up here at the top on the next circle. We ready to move on? We ready? Okay, so this one, and you've got the worksheet. I've got it real small, so just because you don't read it, don't worry about it, because you've got the worksheet. So it says we're going to design and draw a zener regulated power supply that the input is going to, the unregulated input is going to vary between 24 and 28 volts. The regulated output voltage equals 20 volts. And the load current is going to be between 5 and 15 milliamps. So my circuit, I'm going to bring unregulated in. Here's RS right here. This is a positive power supply. So how do we operate zeners? Forward bias or reverse bias? Reverse bias. This over here, I'll go ahead and put a resistor out there, and it's going to vary. So I'm going to put a rheostat. So this guy is going to vary from 5 milliamps to 15 milliamps. My input voltage is going to vary between 24 volts and 28 volts. And first thing I need to do is find me a 20 volt zener. So what zener are we going to use? What's that? Yeah, 1N4749. Are we okay? And then let's go ahead and get the IZK for that so we won't have to go back to it. So what's the IZK for a 4749? 4747? Does everybody agree with it? So y'all, that tells me that 4747, but nobody else is doing it but Brandy over here. 4747. We all agree on the 4747. Yes, no? Huh? You say no? Huh? Yeah, that's why we're doing it with the whole class. Okay, so what would that be? What's that? No, it's on there. What does it say? What did you say, Kareem? 4747. Everybody agree with the 4747 first. 20 vote VZ. So we look in the VZ column and find one that says 20 votes. Okay. And then we're probably going to use an A because we want a 5%. And then we're looking up IZK. And what's IZK for 4747? Okay, but we wouldn't say 0.25. What's that? What would that be? Just move it 3 places. 250 microamps. Just move it 3 places to the right and go to the next unit, right? Okay, so now what's the first thing we need to do? Well, we got to figure out what that resistor is going to drop. So this is a 20 volt Zener. So I'm going to figure my voltage drop, VRS maximum and VRS minimum. So what's the maximum that voltage, that resistor is going to have, I mean not that, yeah, what's the maximum the resistor is going to have to drop and what's the minimum it's going to drop? So what's the maximum the resistor is going to have to drop? Come on, guys. That's one of those head problems. You can do that in your head. Okay, so the maximum is going to be 8 volts. Minimum is going to be what? 4. Y'all understand that? Yes or no? Huh? Yeah, so what we've got here is, and I'm going to go back to this circuit right here. So just think about the Zener being this bottom resistor. And I'm going to say, this guy here is dropping 20 volts. And I've got 28 volts applied. What would this resistor right here drop? According to Kirchhoff's law. It says the sums of the voltage drops in a series loop has to equal to the applied voltage. Well, if this guy right here is dropping 20, I got 8 volts applied. What does this guy right here got to drop? It's got to drop 8 volts because it's got to equal 28 volts. Well, this is the same situation. I'm leaving off this over here. This is parallel. So whatever's across the Zener is across the load. So if this guy's dropping 20 volts, that guy's got 20 volts across it, right? And then this guy right here's got to be dropping 8 volts. Well, what's the minimum? Well, now I'm going to come up here and erase this right here and put 24 volts. Well, if I got 20 volts dropped right here, 24 volts applied right there, and Kirchhoff's voltage law says the sums of the voltages have to equal to the applied voltage. If this guy's dropping 20, then this guy right here is going to drop what? 4. Okay, so I know my voltage I know the voltage that resistor is going to have to drop. And what we're going to do now is calculate what resistor would drop the minimum voltage at the maximum current. Because everything after that would take care of itself. So if the voltage goes up, the resistor is going to drop more voltage and it's going to move away from the knee, right? You understand? So what's the formula? I'm going to go ahead and put the values in while we're doing it. So RS equals, what's the minimum voltage? 4 volts divided by the maximum load current, 15 milli plus 250 micro. Now make sure you put this in parentheses, right? To make it do the math correctly. So what's our calculated value? So this is the calculated value. This is not the used value. Yeah, so it'll do the math right. So 4, don't put the 4 in parentheses, put divided by, just like I got it up here. Then I'd open parentheses, and I'd put 15 times 10 to the minus third plus 250 times 10 to the minus 6, close parentheses, and you're equal. $262. We're going to round down anyway, so putting the 0.9 out there is a waste of time. Okay, guys, so what size would we use? I'm not going to look it up anymore. Y'all going to look it up. What's that? 240? Okay, so we're going to use 240, and then we're going to check the tolerance. We're going to multiply it by 1.05. That's going to raise it up 5%. What does that get us? I don't know. Brandy looked it up. Do we have a 250? Huh? We do have okay. We're looking at the 5% chart. And believe it or not, I need to take the 10% off there. You can't even get 10% resistors anymore. Believe that or not. So about the worst percentage you can get is 5%, and then it goes down from that. So what does that come up and give us? 240 times 1.05? Huh? What's that? 252? Looks like it's okay. What we're doing is shooting for something less than that. If it comes up to be more than that, what would we do? We'd go down one more size. So 240 ohms. Now we're through with this calculated. We're through with that. Y'all understand that? We're through. This is everything else we're going to calculate with the resistor we chose. So this is the resistor we chose. So we know two things about our resistor. We know the value and we know the tolerance because we chose a tolerance. So now we got to make sure we got to choose the wattage rating on the resistor, right? Okay. So how do I calculate PR? We're going to use V squared over R. So I'm going to use 8 squared divided by 240. And what does this come up and give me? Uh, 267 milliwatts. So we'd use 1 watt. We'd use a 1 watt. We'd use a half watt there, right? I got it. What? I don't have the key. Oh, I do have a copy of the key. Okay, I see that. So I got that wrong. So the wattage is actually wrong too, right? You'll see what Brandy's talking about. So that's supposed to be 240, and then the wattage rating is supposed to be 267 milliwatts. Of course, the 220 would work also. What did I do when I calculated the zenith? IZ max. Oh, I calculated it right. I did it right. Okay, so it's just that one right there that I messed up on. So this is what the answer should be right here. Huh? Yeah, we're using 240. That's what we chose. And everything else is okay. It's just when I plugged in that formula there. So the correct answer for circuit 2 for PRS is 200. PRS is equal to H squared divided by 240, and the resistor, the PRS is 267 milliwatts. Okay, now we've calculated that, so we need to check and make sure we're not going to burn up our Zener. So VC is going to be equal to 20. And then, of course, we need to calculate the maximum current. IR max would be equal to 8 volts divided by 240. What does that give me? 33.4 milliamps minus I the load minimum, 5 milliamps, and then that would be our power. Right up here. The formula is, so what we're doing, there's I the load minimum, and then what we do is we calculated the maximum current flow that's in that resistor. If I calculate, and what we're trying to get is we're trying to get the maximum current that would ever flow through that Zener. And so what happens is we look at our laws, and I'm not going to draw current flow. I'm going to draw positive. So if my unregulated is coming up here, then this is one path for current, and this is one path for current. So all the current in the circuit flows through RS. So if I can calculate the maximum current flowing through the RS, then I can calculate the maximum current flow in the circuit. So that's what we did right here. So we took the maximum voltage. So when is the current flow maximum? Well, when the voltage drop is maximum. So I took the maximum voltage that we would drop, then I divided it by the size of the resistor that we calculated. I didn't put that out here. Now that gives me the maximum current flow in the circuit. Okay, so right here we have what? We have 33.4 milliamps. Well, Kirchhoff's current law says the sums of the currents in the parallel branches has to equal to the applied to the current. So we got 5 milliamps going over here, right? You understand? So when would the current flow through the Zener be maximum? Well, it's when the load when the current flow in the load is minimum. Because if I come up here and subtract 15, that means the power in the Zener is going to go down. If I come over and subtract 5, it means the power with the Zener is going to go up. And that's what we're trying to do, is trying to see when the Zener is dissipating its most power. So what do we get here? What? 6.58. You just can't say 6.58. 6.58 watts? So how can I multiply milli? I don't know. So that'd be 20 times, open parentheses, 33.4 times 10 to the minus third, minus 5 times 10 to the minus third, close parentheses, equal, I got 568 milliwatts. Huh? The minus to the third. Yeah. So it'd be different for your calculator. Do y'all use the EE key? Y'all have EE key or EXE key? You got your worksheet, Charles? Well, it's different on different calculators. So we got what? 500 and... So would 1 watt Zener be okay? Would a 1 watt Zener be okay? Yeah, it'd be fine. You got your worksheet, Charles? Yeah. Let me see it. Everybody okay? Yeah, I know back in DC when you was doing all those series and parallel circuits and all that kind of stuff, just wondering why in the world do I have to do this, right? Why? Yeah, and believe me, when we this is an amplifier called a common emitter amplifier. So we're going to start amplifying power. And we'll take our output right here, and we'll put our input right there. What do you think the main formulas we're going to use? And this thing gets power gain. So this guy is an amplifier. He gives power gain. What do you think the main formulas we're going to do to calculate these are? Ohm's law, Kirchhoff's law, right, and the Watt's law. Now we'll have to add a few little things that deals with transistors, but it's not that much. So, you know, and we'll show you how this is basically a series parallel circuit. But well, it's series parallel, but the series elements are so easy to see. So you know, if I came over here and redrew this like this. Of course, it's a series parallel circuit, but that's basically the way that would work. So man, we could calculate this. Hopefully, if you learned it in DC. So you're going to find out that most of the formulas that we learn in these solid state devices are formulas that you learn back in DC, but these are active devices. So a Zener literally dynamically changes its internal resistance to maintain a constant output. So if the current flow goes up in it, it keeps the same voltage drop. If it goes down, it keeps the same voltage drop. It is not a resistor. It is a solid state device. A diode's real easy to see because one way it has almost no resistance. The other way it has almost infinite resistance. So a resistor won't do that. A 100 ohm resistor is what? 100 ohms. So this circuit right here. So we'll draw our circuit, or just a regulating portion of the circuit. We're not going to draw the whole power supply. This is a negative power supply. So we'll come in here and we'll put our Zener in like this. Zeners are operated reverse bias. If you check them with a meter, and that's one lab that we skipped over, we need to go back and do that, and let y'all get that slab on how to check a diode with a meter. If you check a Zener with a meter, it's going to check just like a diode, just like a diode. If you operate it forward bias, it's going to drop 0.7 of a volt. So I got this one. you don't exceed the breakover voltage, it acts just like a diode. It's when you exceed that breakover voltage when it acts like a zener, right? You understand? If you break over a zener, then it's not going to burn up if you choose the right resistor. If this was a regular diode and you broke it over, it'd be gone. So it's designed to operate in the reverse breakover, but when it breaks over, we got to protect it with that resistor, right? You understand? You got your worksheet, Charles? Well, so far we're running 100%. That's not very impressive, guys. Not very impressive at all. I think this is the first class I've ever taught when nobody did the worksheet. Well, no, don't say don't feel bad. You need to feel bad. Well, the problem is when I say does anybody have any questions?
That don't mean it don't sound like you really asking. It really don't. This is the pause I got on it.
Yeah, Zener's not in series. Well, we better get it down right. We better get it down now, right? Y'all understand? So this is getting it down. So there's a lot of on here. We got 2 more to go. If you don't get it now, so the zener is placed in parallel with the load. So when I ask y'all, do I have any questions? It sounds like I don't really mean it. Minus 26 volts. Yeah, y'all better. When I say if there's any questions, and you sit there and like a knot on the log, like Dad used to say. You know. What's that? No, I said there's any questions. When I was in college, of course you got things that come natural to some people, and some things you just struggle with, and this is one of those things that people struggle with. But it just surprised me that basically, well, the formulas you learned in DC, every bit of them. There's no formulas that we didn't learn. So what we're going to do is we're going to look up our zener voltage is going to be no, I wrote something wrong here. I got talking. So let's find our zener. We're looking for a 22 volt zener. There's no such thing as a negative zener or a positive zener. It's how you put it in the circuit. We put the zener to make it act like a zener. We put it in the circuit reverse bias. So if this is minus right here, I've got the anode turned toward the minus, right? You understand that? So which zener would I use? So I'm going to look up a 22 volt zener. 1N 4748. And we'll go ahead and look up IZK. What'd she say? I didn't hear you. 250 what? No, there's none of them that's 250 milli. Might be 0.25. So it's 250 microamps. By the way, when you make copies, they realize when you make copies, you lose that decimal point. So if you ever see in these data sheets, if you ever see a leading 0, then you know there's a decimal point right there. So they start, and you see when I write them up here, I start mine with a 0 too. Huh? It don't say 0.25 milli. Okay, so that's 0.25 milli is 250 micro. Understand, Kareem? Okay, guys, what's the next thing we need to calculate? Okay, so VN minimum. This is not across the, so we're dealing with 26 votes plus or minus 10%. So what, in VN maximum, I'm gonna put the VN max on the top. So what's the maximum it would ever be? Guys, so no, we're not calculating the resistor, we're calculating the minimum and max input voltage. So the unregulated input voltage is equal to minus 26 volts plus or minus 10%. So I'm going to add 10% to that, and I'm going to subtract 10% from that. So what would be my maximum negative voltage? When you do this, by the way, ignore the sign, right? What's that? For what? For what? So you're saying 24.2 is more minus than 26 than a minus 20? So what would be my maximum input voltage that the Zener would see? We're talking about, since this is negative, we're talking about a maximum negative. So what would be the maximum input voltage? What's that? Yeah, but not just 28, a minus 28.6 volts. Is everybody okay on how to do that? Huh? So I'm going to take 26 volts and I'm going to multiply it by 10%. So I'm going to multiply this by 0.1. And that's going to give me a number. It's going to be what's the number? 2.6. Okay, so what I'm going to do now is I'm going to take 26 and I'm going to add 2.6 to it, which is going to give me 28.6. And then I'm going to take 226 and I'm going to subtract 2.6, which is going to give me what? 23.4. Is everybody okay? Huh? Not 20, yeah, it's 26 times 10%, right? You subtract it from it. So here we added 2.6 to 26. Here we subtracted 2.6 from 26. There's another way you can do it. I don't want to confuse you, but it's a little faster. Well, we know if I want to increase a number by a percentage, I can come up here. If I want to increase it by a percentage, I can say 26, right? You understand? And then I'd multiply it by 1 point, then I put the percentage out there. And that would give me the high number. And then this right here would give me 28.6. So if we're going to raise it, if we're going to raise a number a percentage, we just multiply it by 1 point, then the percentage. So that would raise it by, if I wanted to go down, I would subtract it from 1. So if I said 26 times 0.9, so that's 1 minus 10, right? You understand that? Then that would give me 23.4. And that's just another way of doing it without having to do what? Without having to find what 10% is and then add it and subtract it, but it's up to you. So there's our minimum and our maximum voltages. Negative voltages. So we're looking for our maximum negative voltage and our maximum, our minimum negative voltage. Okay, so what can we do now? What do we need? What do we need to find now? What's the first thing we need to find when we design this thing? We need to find the value of RS. So to find the value of RS, I need to find the voltage drop that's going to be across RS. And this is a what? 22 volt Zener? Well, it's a 22 volt Zener. There's no such thing as a negative 22 volt. So all I'm doing down there is putting the VZ. There's no such thing as a negative Zener. Yeah, you always put it reverse bias. So if it's a negative power supply, then your anode is going to point toward the, so instead of me writing down 22 volts to get y'all confused, let me write down VZ equals 22. Huh? No. You always reverse bias it. So here's the negative right here. So to bias a diode, we need to put the negative toward the cathode. Well, here's the cathode right there, Brandon. So we're putting the negative toward the anode, so it's what? It's reverse bias. If we're using it in a positive power supply, we put the cathode toward the positive. Okay, you'll understand that. So to make it operate like a Zener, so if I put the cathode up, it'd drop about 0.7 of a volt. So as long as you don't exceed the breakover voltage of a Zener diode, it acts like a diode. So when I check one with my ohm meter, it checks like a diode. So I can't, when I check it with my ohm meter, I can't tell if it's a Zener or I can't tell if it's a diode, because your meter is not going to break the diode open. So Zeners are silicon. We don't run into any germanium. I've never seen a germanium diode. And germanium we use, if we use second approximation, it drops around 0.7 of a volt when it is forward biased. But here we don't say it blocks the entire voltage when we reverse bias it, because these guys, we operate them to break over, right? You understand that? So I need to calculate my voltage drop across my resistor. So VRS max and VRS min. So what's VRS max? What's that? Okay, we'll do it one more time. One more time. What you got to do when you treat this, you've got to treat it as this circuit right here. Okay. And what I've got, and this right here is I'm going to put that resistor, and this is just for DC purposes. It's not a resistor. But what we're going to do is I'm going to come up here and put my maximum voltage right there, 28.6 volts. And I'm going to say this resistor right here is dropping 22 volts. And here's RS right there. Now, according to Kirchhoff's voltage law, it says the sums of the voltage drops in that series circuit right there has to equal to the applied voltage. So that resistor cannot drop 28.6 volts. It's got to drop what's left, right? You understand? So when we calculate this voltage drop, we're not using this. This is over here. So over here we're putting a minus 28.6 volts, and it's varying between minus 28.6 and minus 23.4. Now what we're trying to do is we're trying to operate that Zener past the knee. Right? You understand that? Okay. So when we choose that resistor, we choose it to drop the minimum voltage, which would be right here. Because if the voltage goes up, it's going to move it that direction right there. That's the direction we want it to move. So that's why we're going to calculate it to drop the minimum voltage. because the maximum voltage is going to move it away from the knee, right? You understand that? So this is why we use the minimum voltage drop when we calculate the size of that resistor. So we need the voltage drop across the maximum voltage drop across the resistor, and not the maximum voltage drop in the circuit. So what would be the maximum voltage drop across the resistor? What's that? Okay, so I'm going to figure out the voltage drop across that resistor. Now, some of y'all got it right, and I appreciate that. But I want you to see that. This guy, I've got 28.6 volts applied to the resistor. It don't make any difference. It's minus or plus. This is dropping to minus 22 volts. How much does that resistor got to drop? It can't drop 22 volts because that would give me 44 volts dropped in a circuit that's only got 28 applied to it. That's exactly right. That's what we're doing. This is VRS right there. That's exactly what it is. It's just Kirchhoff's law. That's all it is. Kirchhoff's voltage law. So if we had done this in DC and I gave you that, and y'all work, how many of those problems did you work in DC where they gave you one resistor drop and you were supposed to figure everything out? Had a lot of them, right? When you was dealing with series circuits. So what would be the maximum voltage drop? What was it? 6.6 volts. That's the maximum that resistor would drop. But what would be the minimum it would drop? So now I'm going to change this out up here, and I'm going to put my minimum input, which is 23.4. This guy right here is still dropping 22 volts. That's what a Zener does. As long as I give it enough voltage to do that, right? So what would be the minimum voltage the resistor would drop? Huh? 1.4? Okay. So we okay so far? So what I want to do now, I'm going to figure the size of that resistor. We want it to drop the minimum voltage. If we drop the maximum voltage in the minimum voltage, it would move into the knee. Right? You understand that? Okay. So I'm going to come up here and I'm going to say, what size the resistor do I have? I'm going to look at my formula sheet and it says RS calculated is equal to the minimum voltage, 1.4, divided by what? The load current. I didn't put the load currents over here. What's the load currents? 10, not amps. 15 milliamp, 10 milliamps and 15 milliamps. So I'm going to use the maximum load current, because if the load current goes down, Zener current goes up. 15 milli plus IZK, which is 250 micro. Which you could use 15.25 micro if you want to. It'd be the same answer, right? 1.4, I mean 15.25 milli, excuse me. Oops. What do we get? So what we got, guys? What we got? Okay, so what got 91.8? Everybody okay? Everybody okay? Everybody okay? You okay, Charles? Yeah, I want you to too. No, I don't want you to get behind. Okay. So what do we need to do now? So now we're going to go into our standard resistor chart, and we're going at 5%, and we're going to round this down. So what's our first shot? Yeah, but 91 will never work. So 91, let's check it. I'm going to multiply, we want to do this. I'm going to multiply it by 1.5, 1.05. And what do we come up and get? Yeah, 95 point what? Yeah, 95.6. Yeah, that's not going to work, right? You understand? Yeah. So what's the next value? 820? 82 times 1.05. And what does that give me? 86.1 ohms. This guy is great, so we're going to use an 82 ohm resistor right there. Yeah, as soon as that came up, we really didn't have to check that. So as soon as I got him up and got 91, we knew that that thing wasn't going to be right? Going to use an 82 ohm. Yeah, we started out with 98. We looked in the chart and found out that the next lower value was a 91. We always go down, right? Then we checked our tolerance, just like it says there. We multiply it by 1.05 so that's going to increase it. We don't worry about it being low. We worry about it being high. If it's low, it's no big deal. If it's low, it's going to move it out of the knee anyway, right? So when we use 91, which was the next one in the chart, we came up with 95.6 ohms. It cannot be larger than that, so we went down to the next standard value, which was 82 ohms. We checked the tolerance on that. It came up to be 86. It was less than that, so that's what we're going to use. Okay. So we've chose our resistor. And we know two things about the resistor. We know the value and we know the percentage, right? I mean the tolerance. Because we chose the tolerance. What's the third thing we got to do before we buy this thing? We got to calculate the power rating. The watts. So we're going to use V squared over R. So power RS would be equal to V squared, the maximum voltage it would ever have to drop, 6.6 squared, divided by the value that we chose, divided by 82. So PRS, the wattage rating on the resistor, has to be at least I don't know. I don't have my formula sheet. What's that? 532 milliwatts. So we'd use a 1 watt Zener there. Are we okay? We okay? We okay? Well, it's going to be one of our answers. We're not going to use it in any more calculations. You're right. But that's one of the answers that we need to figure, right, Courtney? Okay, so now we need to calculate the power in the Zener. So I'm going to calculate the maximum current in the resistor. So IRS max is when it's going to drop its maximum voltage, which is going to be 6.6 volts, divided by the size that we're using, 82 ohms. You can do this. You could do this as part of the formula, by the way, if you wanted to skip this step right here. I'll show you that in a minute. So the formula is PZ equals VZ times IRS max minus I the low minimum Well, you could say, you know, PZ would be equal to BZ, and then you could say, inside here, you could say VRS max over RS minus I load.
So we don't have to do the
It's just, it's not another way, it's another way to check your answer, but we gotta do PZ. We gotta calculate Zener power. Why do we have to calculate Zener power? So you want to make sure you don't burn up. So we're using a 1 watt Zener. So if this answer comes up to be more than 1 watt, what does that mean? That means we would burn the Zener up in this circuit. And that would tell me I need to find a Zener that has I need to find a 22 volt Zener with a higher wattage rate. We gotta calculate the power of the resistor. Now, I know I told you about the power supply class I taught, right? Where they kept burning up 100 ohm resistors. And they came up and kept blaming it on something's wrong with my power supply. It keeps burning up these resistors. But what they did is they just got a little old quarter watt, 100 ohm resistor, and they was putting across a 30 volt power supply. And what would that be? So 30 volt power supply, I'm going to take 30 and I'm going to square it and I'm going to divide it by 100 ohms. So that's 9 watts. So that's putting a quarter watt Zener on a circuit that was developing 9 watts worth of power. And what did it do with the Zener? I mean, with the resistor, just burned it up. And what was they doing? They was blaming it on their power supply. But they never calculated the resistor. And this is something we probably need to teach way down there, where when you buy that resistor, you got to know 3 things about that resistor when you buy it. And what's the 3 things? The value, the watts, and the tolerance. You got to know that. And what things do we need to know basically about the Zener? We need to know 3 things about the Zener. Not the physical size. VZ, right, you understand, the wattage rating, and the tolerance. And then we calculate everything around IZK. We'll have to look IZK up in the data sheet, but we don't have to specify an IZK, right? You understand that? Well, the only thing we use IZK for is to calculate that resistor. So if I go out and I say I want a 1 watt, 10 volt, 10% Zener, and then I look at the data sheet to calculate the resistor. So that's 3 things we need to know about a Zener. What's the 3 things we need to know about the Zener before we buy it? We need to know the Zener voltage, we need to know the wattage rating, and we need to know the tolerance. So actually, we're actually using this guy right here. So somewhere on that data sheet, down below that, it says if it's got an A, it's a 5% tolerance. If it don't have an A, it's a 10% tolerance. So that's the only thing. The only 2 tolerances this guy comes in is 10% and 5%. So if you look down at the bottom of the data sheet, let's say that. So let's do that. What do we get for this right here? What's our RS max? 81 milliamps. Okay. So we'll come up here and calculate our Zener. So PZ would be equal to 22 volts times, open up parentheses, 81 milli minus 10 milli. So what's the power? By the way, here's, you don't have to use parentheses. You can do your subtraction first, right? Because it don't have a divide. 71 watt? We're calculating power, correct?
No.
Oh, okay, yeah. Yeah, you can do that in your head. Times 22, so, yeah, I see that now. That's fine.
1.5 watts.
Don't make any difference. We burn our Zener up anyway. Why? So what's the wattage rating on a 4748? So 1 watt Zener. And this circuit is going to give us 1.5 watts. So that means we can't use this Zener. So what would we do? We're going to calculate it. What would we have to do? If you go down with a resistor, you're really going to burn it up. What would we do? What would we do? I just told you a while ago. This is the power supply. This is the power supply. This is the power supply I want. If I go down on the voltage, it's no longer the power supply that I want. So this is the power supply I want, but I cannot use a 1N47, a 48 Zener. So what would I do? What'd you say? I'd change the Zener. That's exactly right. I'd find a 2 watt Zener. I'd go on the internet and I'd say a 2 watt Zener. And it would pop up a part number up there for me, and that's the one I would use. And then, right, you understand? Couldn't add another resistor, because then if you add another resistor, then you change the circuit, you change the design characteristics of the circuit. Where would I add it? If I lower the current, you say, why don't you lower the current? Well, then it's no longer the power supply I need. Right, you understand that? So when you design a power supply, what do you design your power supply around? Yeah, what you're gonna run? What is this power supply's got? What's this regulated power supply got to run? And then that would set what? That would set this. That would set everything. That would set your transformer, right? You understand? That would set everything down the line. Of course, these guys you can't do very much because they're not designed to handle a lot of current. 15 and 10 milliamps is not much of a load. It run an LED, great. I don't know what you mean by universal power supply.
Like power towards my laptop. Power supply. So I went to
Yeah, and it had a bunch of different connectors. Okay, so what about it?
I don't know how to like a I don't see that on the whole other.
Well, it's not. It's just somebody designed it, right? You understand? So we need a 22 volt supply. What's the odds of me finding a 22 volt supply? Probably slim to none, because they come in standard ratings. You know, we can find a lot of 12 volt power supplies. We can find a lot of 5 volt power supplies. We can find a lot of your laptops run on 20 volts. So I can find 20 volt power supplies. I can't find a 20 volt power supply. I can't find a 50 volt power supply. I can buy a variable power supply that gets up that high, but I'm going to be paying tons of money for that. How much did that universal power supply cost you? About 40 bucks. We're talking, this guy right here, for this screen right here, we're talking maybe $10. It's all about the cost. Yeah, these dang switching power supplies, they're really nice. And I'm going to show you all a switching power supply. They're nice. Buying a power supply is going to cost you a lot of money, right? You understand that? And there's a lot of places that do that. If we go over there and look at the Amatrol line, or if we look at the Festo line, those are bought power supplies. They didn't design those; they bought them. Well, I think they're Siemens power supplies, and they got Siemens PLCs. But Siemens-based power supplies, sure. But they're always going to be a fixed value. So you get into these strange power supplies, like your amplifier in your car, like your car radio. That's probably not a standard power supply. So they had to, that power supply is built into your radio, of course. Don't understand that?
I thought we
About what? Oh, yeah, for the, yeah. Yeah, I did get the link for Sarah Versa, right? Yeah, and it upset me. One of the things that we're trying to do is to bring in non-traditional students into our program. So Nancy made sure that we had two ladies that interviewed. Randy was one of them, and then Brittany was the other. And guess what? They put two males on there.
Yeah, that's
That
she was there.
yeah, she did a good job too. She did a really good job. She did a real good job too. You know, why she chose the two males, I don't know. I wish she would have chose. I put James in team, but see they chose two males. I wish they would have chose one male and one female, and then that way it would let the females know y'all need to take a break. It would let the females know that out there that this would be a career choice. Yeah, go take a break, guys.